I'm a professor at the University of Connecticut, and I am moderating this session on emerging mobility services planning and operations here at the 2021 CAMMSE annual symposium. So our first speaker today, we're going a little bit out of order from the program, but our first speaker will be Dr. Yi Chi from Texas Southern University, who's going to speak about an innovative signal timing strategy for implementing contraflow left turn lanes at signalized intersections with split phasing. So Dr. Shi, please go ahead and begin.
Okay, sure. Let me share my screen first. Okay, so where's my, okay, share. Okay, let me pull out my presentation. Okay, can everyone see my PowerPoint slides?
Yes, we can see.
Okay, wonderful. Okay, good morning, everyone. It's a pleasure to be the first speaker of this technician section one. Okay, so I'm Yi Chi from Texas University. Today, I'm going to talk about the contraflow left lane intersection signal design again. So if you attended last year's symposium, you may remember I already introduced this innovative intersection design last year. And at that time, we talked about the general signal timing design. And since then, our team has done more work on this topic. And we find some very interesting findings. So we would like to share with you today. Okay, here's the outline of my presentation today. First, I'm going to introduce the background again. So I will talk about what is contraflow left lane design, what its benefit and the limitations again. After that, I also will introduce a special signal timing, which is called split phasing. So after the background introduction, I'm going to talk about the problem statement, what kind of problem we found, and also our research goal. Then I will present our solution, innovative new signal timing strategy for this type of intersections. After that, I'm going to use a case study to show the benefits of using the signal timing strategy we proposed. Finally, I will give you the conclusions of this study. Okay, so this is outline. So let's start with the background introduction. Okay, I know I already introduced this design last year, but just refresh.
Yeah, I can mute.
Hello? Everything's okay? Hello. Okay. So this is the design we learned last year. So let me briefly introduce it again. So this is called the contraflow left lane design. The whole idea of this design is at a signalized intersection, if we have heavy left turn traffic, we want to use more lane to move the left turn traffic. So in this way, we can temporarily using the opposing through lane as a dynamic left turn bay to move left turn traffic. So in this way, the left turn demand can be capacity can be doubled. Okay, then the congestion and the delay can be reduced. So this is the whole idea of the design. So you can see in this graph, I show the design of the intersection. In this design, the key thing is we want to make sure the left turn and the opposing vehicles, they both use this control left turn lane will not have conflicts. So we needed to design our signal carefully to make sure there's no chance these two movements will be used the contraflow lane in the same time. So for this purpose, we installed the pre-signal lights at this media opening upstream of the intersection to control the vehicle and the contraflow left-hand lane. And this 4 pre-signal lights have to coordinate with the main signal lights at the main intersection to make sure everything will work properly for the contraflow left-hand lane design. So this signal timing we used to control the traffic at the contraflow left lane intersection. We have introduced this design last year, how we developed this signal timing. So this is the things that the people use now. And basically we use it for the lead left turn signal phasing. So in the lead left signal phasing, the left turn always move first. So the control flow traffic will enter the control flow left turn lane during a pre-signal phase. So you can see the pre-signal phase. For example, we use the sourcebound left turn as example. So the sourcebound left turn, here the solid line of the signal timing plan is the signal phase at the main intersection, and the hollowed arrow indicates the left movement at the pre-signal lights. So you can see for the sourcebound, the pre-signal lights, the 7' will start when the crossing streets have the through movement, like the phase 2 and phase 6, this for east and westbound traffic moving. So when this signal starts, the pre-signal lights will turn on, then the left-hand vehicle can enter the control flow left-hand lane. So after that, the signal will switch to the north and southbound, then the left turn will start, the left turn signal will turn on, then the vehicle from the control flow lane can be discharged from intersection. So this is the way this type of intersection works, and we use signal to control them when they should enter the control flow, when they should be cleared. Then once they clean from the intersection, we can release the opposing traffic. Okay. Here's a simulation to show how this type of intersection works. So let me play it. You can see the first is the through movement in the main intersection, stream. You can see at that time the cross stream have vehicle enter the control flow left lane. Then the control flow left lane left turn was released from intersection. So after that is the through traffic from the crossing street. Okay, after that is the left turn from the main street. Okay, so this simulation can show you how this type of intersection works, how this signal designed for this intersection. Okay. Now let's talk about why we use this intersection. As I mentioned, the first, the benefit is it can, double the capacity of the left-hand vehicle at the intersection, so it can reduce the delay and the congestion. Another major thing is you can see this type of innovative intersection is quite easy to implement. You don't need to have a major constructions at intersection. What you need to do, just put some signal lights in the middle opening as a pre-signal lights. Then you mark put some pavement mark to indicate this control flow left lane. So it's quite easy to implement. And another thing is also quite easy to convert back. If people don't like it, most of the time this kind of innovative design will make Java confusing. So some people may don't like it. We can easily take it back. Okay, so that's the benefit for using this type of innovative intersection design. And as a result, it works quite well, actually. It has been widely used in China. Okay, in many cities, they have this kind of intersection design has been implemented, and the results is quite good. Sorry. Sorry. Okay, then I think for this type of design, the major thing is the safety. We want to make sure everything operates safely because we allow the two traffic flow use the same lane. So there's potential conflicts between the control flow left-hand vehicle and the opposing vehicle. Besides that, it also makes conflict with the turning movement from the side street. Okay, so all these things have to be carefully designed to make sure this kind of conflict will be avoided or will be prevented. Okay, so another limitation we find, because all the things I talk about is we presented last year. So now we talk about what's the new findings. So the new findings, we find there's a limitation for this type of intersection design. First, it can only work with the intersection with the lead left-turn phasing. So we know if you have a exclusive left-turn phase, there are three types of sequence: lead, lag, or lead, lag. So I show this different sequence in the screen. So for this design, lead, no problem. They only can use the lead. But if you have a lag, or lead, lag sequence, it can't work with it. The reason is if for any lagging left-hand phase, before the left-hand phase, you move the opposing through traffic. So because you are moving the opposing through traffic, you are not able to move the left-hand vehicle into this control flow left-hand lane. So in this way, this control flow left-hand design will not work. Okay, so in the real world, what people do is, okay, if I want to use the control flow left-hand design, I just change the sequence. I change all the sequence to lead, then we can use for control flow left-hand lane. However, in some case, that might be a need. We have to use lagging phase. For example, we have this split phasing. So let me introduce what this split phasing is. So split phasing is a signal timing design that assigns the right of way to all movements of a particular approach, followed by all movements from the opposing approach. So basically, in the split phasing, we totally separate the traffic from both directions. So we release the through and the left turn first from one direction, then we stop all the traffic, then we release traffic from another direction. So for this kind of split phasing, you can see we have to have one direction is lagging. Okay, so let's talk about why we have to use split phasing. Okay, so there are some needs. Some type of intersection we have to use split phasing. The first, because some special geometric conditions. For example, at some intersection, you don't have space for exclusive left-hand lane, but meanwhile, you also have quite heavy left-hand traffic. So in this kind of intersection, we usually use split phasing. The reason is when we use split phasing, we don't need to separate left turn and the through traffic. We can move them together. So in this way, we don't need to separate the left turn vehicle from the through vehicle. So we don't need to have an exclusive left turn lane. Okay, so this is one case we need to use split phasing. The second case, in some time, because of the intersection geometric condition, the two left-hand paths will be overlapped. For example, a skewed intersection. So in this way, it's not safe to allow them left to move together. To prevent the left and from both directions move together, we use split phasing. Okay, so this is the geometric thing. Sometimes some special traffic condition which also recommend us to use the split phasing. For example, if we have an intersection, the traffic for the left-hand lane and the through lane is quite balanced. That means the number of vehicle per lane for both through movement and the left movement for the same direction is close. And meanwhile, the traffic for the both opposing direction is quite unbalanced. So this happens a lot. We have unbalanced traffic for both directions. So in this case, it's better to use the split phasing than the regular, left-hand design, left-hand phasing design. The split phasing can more efficiently use all the signal timing, all the green time allocated for the other movement. Okay, so there's a case the split phasing have to be used or have some benefit. So the problem, since the CLL design cannot be directly used at the intersection with split phasing because we have to have a phase lagging. So in this way, we cannot, for the intersection with split phasing, we cannot have the same benefits using the CLL design. Note that, as I mentioned, the split phasing also usually used at the intersection with a higher left turn volume. So it will be nice if we can also use a CLL design at the intersection. There are the needs for use of split phasing. Okay, so how we solve this problem? So the goal of this research is to develop an innovative signal timing strategy for implementation of CLL design at intersections with split phasing. So if we develop such a signal timing strategy, it can combine the advantage of the split phasing and the CLL CLL design, then we can achieve more operational and safety benefits at the intersections where the split phasing is recommended or required. Okay, so this is the goal of this research. Then let's talk about our design. So this is the new innovative single timing design we propose. It's different with the regular single timing design, because in the regular single timing design, we always release the approaching from the both directions, and we switch to the side straight. So this time we call the new single timing design, we call it counterclockwise split signal timing. So here is what it works. So it allocates signal around the intersection in this counterclockwise direction. So first, we move the northbound traffic. Okay, so we move the northbound through and the left turn. Meanwhile, we have the pre-signal in the westbound turned on. So the westbound traffic can move into the control flow left lane. After that, we switch the signal to the westbound. So the westbound left turn and the through vehicle can be discharged from the intersection. So same thing, later we switch to southbound, then we switch to the eastbound. So finally, we switch the signal back to the northbound. So you can see in this single timing design, the pre-signal lights always turn on right before the signal switch to that direction. So in this way, we can we can allow the vehicle enter the control flow left lane to waiting for the left turn signal turning on. So here I present the single timing diagram for this type of new design. Okay, so this is the basic idea. We also develop a detail of, okay, let me show you the simulation, see how this thing works in the simulation. See this first, then the next one from the side street, then the major street again, then the side street again. Okay, go back to the major street. Okay, so this is the simulation to show the operation of this is the proposed new signal timing design. Okay, so we designed a detailed procedure, a 5-step procedure to develop a signal timing according to the idea we proposed. So I'm not going to go to very detail for each steps because the whole idea is similar as the signal timing design strategy we proposed last year. The whole idea is we want to make sure the left turn and the opposing will be, safely separated. There's no way the left turn vehicle can be, trapped in the left control flow left turn lane before we release the traffic from the opposing direction or from the side street, turning movement. So this is the whole idea. So if you are interested, you can take a look at the paper we published. You can search the name of this presentation in the Google Scholar. You will find the paper we published recently on this topic. Okay, so what I'm going to show you in today's presentation is show you a case study to demonstrate the benefit of using the proposed CSP signal design. So we use a hypothetical intersection to show how this signal timing design works. So this is a hypothetical intersection we designed. The reason we designed the hypothetical intersection because we want to make sure the traffic condition is the condition that really needs the split phasing, that's perfect for using the split phasing. So you can see in this intersection, we have each direction, the left turn and the through traffic is kind of balanced in terms of the vehicle per lane. They are very balanced. And also for the two opposing direction, the southbound have less traffic than the northbound, and the westbound have more traffic than the eastbound. So they are unbalanced for the both opposing direction. So according to traffic condition of this hypothetical intersection, we designed the split signal timing for this intersection. So this will be a baseline situation. We can do the comparison. Okay, so then we converted this intersection to a control flow intersection. So you can see we add 4 control flow left lane here, and then we also added the pre-signal timing at the media opening. Okay, so after that, we need to design the signal timing. There's 2 ways we can make the signal work for this location. First is use the CSP signal timing strategy we proposed, which is still keep it a split phase, but make it a movement like a counterclockwise movement. Then the second one is we just use existing signal timing strategy. This is a strategy used by all the existing research or the practitioners right now. So we convert the thing instead of split phasing, we use lead left and phasing for this intersection. Okay. So these are 2 different types of signal timing for this intersection. Then we started to do the traffic simulation to see how these different type of signal timing will work and the different traffic conditions. So we tested 3 things. First, we want to test if we change the whole traffic volume for the intersection, what will be the performance of this signal timing strategies. Then we also change the left-hand volume because we know the CL lane design is mainly for the intersection with heavy left-hand volume. So we gradually increase the left-hand volume for each approach. The third one, we also changed the unbalanced traffic conditions, the level of unbalanced traffic conditions for this intersection. We want to make the already unbalanced traffic condition more unbalanced to see what will be the results. Okay, so let me show you the results. For the first results, we just we changed the whole intersection traffic volume. So you can see in this graph, we have the average travel time and average delay and the different scenarios. And the horizontal axis shows the traffic volume for the whole intersection was gradually increased from 100% to 140%. And these 3 lines represent the 3 different, signal timing strategies. The first line, the light solid line, is the existing condition, the one with just a split phase, no CL, no control flow left lane. The second one, the dashed line, is the one with CL design, but we use the lead left phasing as other research using. And then the last one, the solid, the dark solid line, is the signal timing strategy we proposed, the CSP signal strategy, and also used with the control flow left lane design. So from both graphs, you can see the solid dark line is the line in the bottom. That means the signal timing we proposed will result in less travel time and less delay. So it was performed better than the existing, signal timing strategy for the CLL lane design. Okay, so then the next one, we also change the left-hand volume. In this time, we keep the through volume thing, but we gradually change the left-hand volume for each approach from 100% to 150%. So the results is similar like the scenario 1. Our signal timing strategy is better than the lead phase-based signal strategy, and the scenario you just use the split phasing without the CL lane. Okay, so you can see from this graph, you can see with the left volume increased, the benefit using the CL lane design also increased. You can see the difference between the first line and the rest of the 2 lines become bigger. Okay, so that's reasonable because the CL lane design is to help reduce the congestion caused by the left-hand traffic. Okay, then we go to the last one. The last one, we try to see if we make the traffic more unbalanced, what will happen. So in this intersection, we can see the westbound traffic is heavier than the eastbound. So in this time, we gradually increased the westbound traffic from 100% to 160%. So in this way, the traffic in this location will become more unbalanced. So you can see from this graph, this is the signal timing we propose as a solid dark line, you can see with the westbound traffic increased, the difference between the signal timing we proposed and the signal timing currently used for the CAMMSE design become bigger. So they become more and more big. That means with the traffic become more unbalanced, our signal timing strategy have more advantages. This is also reasonable because with the traffic more unbalanced, we should use the split phasing instead of the lead left phasing. So that's why our signal timing works better. Okay, so this is all the major results we got from simulation. It looks all reasonable, and also it shows the benefit of using the proposed CSP signal timing design. Okay, here is the conclusion. By using the proposed CSP design, the control flow left-hand design can be implemented at the intersections where split phasing is recommended or required. So we solved the problem we raised before. So the benefit of the split phasing and the CL design can be combined at those intersections. Second, we also find the use of the proposed CSP signal timing strategy and the CL design for the intersections with split phasing can significantly reduce the traffic congestion at these intersections, especially at the intersections where the traffic volume on both opposing approach are very unbalanced. Okay, so this is the major findings we got from this research. Now I'm open to your questions. Thank you.
All right, so we just have a few minutes for just a couple of questions, if anybody has. Okay, well, I had a question, Dr. Shi. So I wanted to, I'm curious about how do how do you handle the right turns while the left turn, while the left turners are pulling into the advance, as far as where you're queuing them up for their phase during the pre-phase? How do the right turners, how do you deal with, because it seems like they're both going to be traveling in the same roadway, and how do you make sure they know what to do?
Okay. This is a very good question. Okay.
Especially with your what do you call it, the counterclockwise phasing, because they would be going at the same time for sure.
Yes, that's a very good question. Thank you. And we talked about this issue in the last symposium, and we needed to use geometric design to separate the right turn and the vehicle on the control flow left lane. So the solution we propose is to use channelized the right turn. Only allow the vehicle move in the right turn channel. Another thing we need to let me see. Okay, so yes, the right turn, you are right. In the Contraflow is exactly the same time they have the green lights. Yes. So channelization will be the suggestion we gave. And also,
okay, there's a question in the chat as well.
Yes. Okay.
It says, what are the expected impact of fuel consumption or emission from the contraflow intersection design compared to conventional intersection design?
Okay, that's also a very good question. Yes, as I mentioned, the contraflow intersection, it can use the opposing left lane to move the left traffic. So it will increase the capacity and reduce the delay and the congestion. Because the delay and the congestion at the intersection was reduced, so the emission, fuel consumption also will be reduced. Consequently, because we have tested the simulations as a result for the emission also can be pulled out from the simulation. The results also indicate the use of contraflow left lane can reduce the emission and the fuel consumptions.
Okay, good. Thank you very much.
Yeah,
all right, so why don't we move on to the next panelist now. Thank you very much for that presentation. We'll move on now to what would have been the first presentation for the session, which is by Dr. Randy Machemehl at University of Texas at Austin. And his topic is developing smart traffic signal control. So So Randy, I'll let you go ahead now.
Okay, John, thank you. Let's see. All right, I'm gonna try to share my screen here. All right, can everybody see my screen?
Yeah, so you can see it.
All right, very good. We're talking about traffic signal timing, so we'll continue basically from the previous presentation. And basically, the problem that we have with traffic signal timing is essentially always the fact that traffic demand is highly variable. The typical intersection has to deal with something as you see on the left here, which might be a peak time period. And then in the evening, that same intersection could look like this with no traffic at all. And the traffic signal controller has to deal with that. City of Austin maintains about 1,100 signals in the Austin area. And most of those are fixed time signals, but they're all interconnected. And they typically have 5 different signal timing plans to compensate for the fact that during peak hours, the cycle lengths and the other characteristics are very different than they are during off-peak or nighttime hours. But in talking to an engineer with the City of Austin, he emphasizes the fact that the traffic demand is highly variable, but it is systematic. And he said, I get about the same kind of traffic demand across the hours of the day from pretty much all weekdays. Weekends are different, of course, so they run different signal timing plans on weekends. But there's a lot of systematic characteristics that are helpful to signal timing. However, within the network, there are incidents that occur on a regular basis. Sometimes they're crashes like this, sometimes they're disabled vehicles, sometimes there's simply an object dropped in a lane. And these cause unexpected capacity reductions. And I imagine we've all sat in congestion that has occurred as a result of an incident and wondered why the traffic signal doesn't respond to the change in demand. Well, if you change the capacity, of course, then it would make perfect sense that the signal timing should change. But in most cases, that doesn't happen. So over the last year and a half or 2 years, we've seen traffic congestion decrease almost to a non-existent situation. But at least here in Austin, we're seeing urban network congestion return. And so I'd say we're about 85% of the way back to the congestion problems that we had before the spring of 2020. And so there's a need to deal with network congestion issues without a question. And we've been experimenting with machine learning as a way of controlling traffic signals. Machine learning is becoming more feasible as computing power is increasing and the cost of that power is decreasing. Data collection technologies are improving. We've advanced a long distance from the situations that we had a few years ago, in which the only detection capability was an inductance loop detector. Now we have all kinds of radar and video-based detection systems that allow us to do almost anything, detect almost anything that we want. And as all this is happening, data storage costs are decreasing. And so these are the 3 primary elements that machine learning requires: a significant amount of computing power, data collection that provides real-time input to the controller, and data storage, where data storage is really sort of emulating the effect of our brains. More about that later. There has been quite a lot of work done on intersection control using machine learning, but virtually all of that work has not really dealt with the problem of traffic pattern disruptions caused by traffic incidents. And so that's where we're particularly concentrating our effort. Our goals are to build a microscopic traffic simulation framework talk more about that in a moment. Develop an incident or emergency vehicle response module that impacts the network by emergency vehicles that are responding to an incident. Develop a machine learning system that works for a single intersection, and then apply that deep learning concept to a network. And in that network, we'd like to be able to get this signal to respond to traffic incidents. And so the first thing we had to do was find a microscopic traffic simulation tool that we could use here. Most of you probably use off-the-shelf simulators, CoreSim or VSim or others. And Tai-Chin Lee, the guy that's my doctoral student who's leading this effort, learned about an open source, free open source micro simulator called Sumo summer before last, as he worked for another agency. This guy has existed for about 20 years. It'll run on Windows, Macs, Linux, or any other system, or most other systems that you would like. It has contained within it an ability to allow the user to specify just about any sort of traffic signal control algorithm that one would like. We've done that sort of thing with CoreSim in the past, and this is much, much easier to do than it is with the patch in to CoreSim. And of course, it has built into it a grid network generation module. It does animation. You can do 2D or 3D animation. This actually looks a lot like CoreSim, but it's actually from Sumo. So we're using this, and I should note that there are some advantages and disadvantages to using this kind of a simulation package. The advantage is, of course, we can make it do anything that we wish. We can describe any kind of a traffic control situation that we would like. We can build into it the machine learning process. The bad news is this simulation software does not bring with it all the things that come when you use CoreSim or VSim. That is, you have to tell it where the vehicles enter the system. They can enter any place that you want them to enter. At one point, we had vehicles entering at mid-link. Not really a very appropriate process, but at any rate, there's a lot of detail that one has to put into this thing to get it to behave the way that we really expect the real world situation to behave. So there's effort required to set this guy up, but it is totally flexible. And so the flexibility is what we were looking for here. It is rather fast as well. We're looking for speed. And in this problem, we're using a grid network. And again, the concept is what happens in the grid network when an incident occurs somewhere inside this grid network. And we intend to have a machine learning signal controller process running at every intersection in the grid network. To help our machine learning system learn, we're going to generate demand randomly. And in terms of our emergency response vehicle module, we're going to randomly choose the location and time of incidents. We're developing a Sumo module. In fact, we've already developed that module. We're randomly generating the incidents, and we're also randomly generating response vehicles. And the response vehicles enter the system from around the periphery of the grid network, but at random locations. And the idea behind this randomness in terms of location and time of vehicle, emergency vehicles and their impact on the network is to allow our machine learning algorithm to learn. And again, the more experience it has, the quicker it can respond. The incident module that we're developing here consists of incident vehicles that are randomly selected. That is, the vehicles that are involved in the incident are randomly selected. The incident location is randomly selected, and the incident durations can range from 15 to 60 minutes. And so we create these things, and we get the traffic signal controllers to respond to them. So basically the sequence of events: the system detects an incident somewhere in our network. Emergency vehicle is generated and dispatched. It's randomly generated from the network fringe. We can change the vehicle length. Right now we're generating only one vehicle, but we can change its length to represent multiple service vehicles. And that service vehicle is stopped at the incident location for the total incident duration. And again, the idea is get the network to respond to this capacity reduction. Talk a little bit about deep queue learning in our traffic signal control scheme. In the deep queue learning process, the term environment, agent, state, action, and reward are used, and I'll use those several times here in the following slides. In our case, the environment is really the intersection. Again, a single intersection. The agent is the traffic signal. The state, and as we're describing states at this point anyway, state represent queue links that are collected by sensors on all the approaches to our intersection. Action basically is to either maintain the current green phase or shift to another green phase. And the reward is delay reduction and the cumulative expected delay reduction. Inside reinforcement learning, we talk about the environment, which our case again is the intersection, and the agent, which is the signal controller. And as the agent makes decisions based upon its experience, and again, the agent acts very much, I guess we could use the analogy of a human brain. When a state comes to the agent, state in terms of queue links on the approaches to the intersection, the agent looks back into its memory and tries to figure out what will be the best action based upon previous experiences. And so this agent gets smarter and smarter as it has more and more experience, just like a human being as an infant, as a baby. We don't have very much experience, and so it's very, very difficult for infants to make very good decisions. And as we get older, we have more experience, and we can look back into our brains and choose the best action for any particular situation that we're in. Well, at least maybe we can. There are some issues we have to deal with there. The number of states that the agent has to deal with here is large, but it's finite. And it's large, the number of states, these are the combinations of states and actions that the controller remembers from the past. For a single intersection, the number of states and actions is large. When we get to a network, it's much, much larger. And so we've had to modify the way our controller remembers the combinations of states and actions. And we've actually moved from a lookup table to another process, which we'll talk about in a moment. The queue learning process consists of modeling the free reinforcement learning algorithm to determine the value of each action for each particular state. And this little equation explains essentially how that's done. This is the new state action, and it comes from the O value, which is the previous time step, plus an impact of the anticipated future activity. This term right here is the temporal difference between the old value and the new value. And it has as a coefficient here, this alpha guy, which is the learning rate. The learning rate has a great deal to do with how rapidly this learning process occurs. As the alpha value, and the alpha value varies from 0 to 1, as the alpha value gets larger, then the impact of this temporal difference becomes greater and greater. As the alpha value becomes smaller, the impact of this difference becomes smaller and smaller. Basically, the learning rate, the reason it's called learning rate, when the learning rate is large, the guy learns fast, but it may miss a lot of potential choices. So the larger the value of alpha, the faster the system learns, but it doesn't necessarily get a lot as, it doesn't increase its intelligence as rapidly as we might like. Make the learning rate smaller, it doesn't learn as rapidly, but what it does learn is likely to be very true. So anyway, learning rate has a lot to do with how this guy behaves. And this is a little piece of code about how the whole thing works. It's a loop. And again, the alpha value, which is the learning rate, varies from values of 0 to 1. The smaller the value of alpha, the slower the thing learns, but the more accurately, you might say, it learns. And again, as long as we were working with a single intersection, we pretty much have the single intersection version of this guy working pretty well. And while we were working with a single intersection, we were able to use the lookup table concept quite effectively. But as the number of potential actions, that is the experience of the controller, increases with the change from a single intersection to a network, we found that the lookup table was really not very efficient. And so we dropped the lookup table and replaced it with a deep neural network. The deep neural network does a better job of connecting the states and actions and results. And it's like improving the ability of our brain to remember, and allows the lookup system to work much more efficiently. So we're using for the network, deep neural network. We have a series of hyperparameters that control the way the process works. Episode is the number of simulation runs that we use. Learning rate, we've talked about that quite a bit. And basically it influences how much the old versus new value affect the future forecast. The neural network size, number of hidden layers, number of nodes for each hidden layer. The batch is the number of data records that we use for updating the model, and an epoch is the number of times the neural model is updated by the data records. The deep Q network variations run into a couple of issues where we could call them problems. And the first of which is that we have lots of sequences of highly correlated states. And this is to be expected with any signal timing problem. Just thinking about a single intersection, when the model passes through the loop, it has to make a decision about whether to stay with the existing green phase or change to a different green phase. And for many time steps, the likelihood is high that the decision will be don't change. So for all of those time steps then are stored in the neural network. And so we get a whole series of decisions that were the same for a sequence of events. And so the chronology of decisions made by the signal controller, basically it's sort of like thinking about an optimization problem with a hill climb process. When the hill climb process finds a point that looks like it's near the optimal value, everything near that optimal value, near that supposed optimum value, is going to be similar. And so the hill climb process then tries to jump to a different spot in the sequence to get out of that supposed minimum condition to find have a better chance of finding the global optimal condition. So it's a similar problem here. A lot of, for signal timing, we have a lot of highly correlated states, and we try to deal with that in terms of a random sampling process that gives us a higher priority to choose terms that have less error. Another issue that we have is of course, we're estimating here, and frequently we overestimate the true action state value. And so we've adopted a double network process. The basic Q-learning process is shown by this equation right here. Again, this is the new value that we're trying to get out of a particular pass through the system. Here's our learning rate, and here's the temporal difference. And we're using a double draw process that gives us a higher probability of estimating the true value that will likely occur in the future. It improves the likelihood of not overestimating the true action state value. And what that basically means is, for basic deep Q learning, the selection and the evaluation process are utilizing the same values, the same network. For our double draw process, we use the term target network to refer to the second draw from the system. And again, this improves the likelihood of not overestimating the value of any particular action. We're applying the deep Q learning model. Again, we started with a single intersection, and this chart illustrates the cumulative negative reward and how that reward increases with the number of episodes. And this is simply showing how the model learns. In the beginning, it's rather slow, and it doesn't really show very much rapid improvement. But as the number of episodes increases, just like the human brain, it gets smarter and smarter and smarter. And so after we get to a fairly large number of episode runs, it is able to respond with a much better value. We refer to states, and states are the maximum Q length of each of the approaches. Again, the only measure of effectiveness that we're using right now is Q length. The actions, and we've limited the signal timing schemes to a fairly simple system for the time being. We're using at every intersection 4 signal phases to deal with the straight right movements. That is, the north-south has a green phase, and the east-west has a green phase. And we're allowing 2 protected left turn movements. The protected left turn movements are basically dual lefts, and they, of course, basically require to work properly left turn lanes. And so we're assuming that those are available. The reward is expected total system delay reduction. And so the single intersection problem, as I say, we have pretty much working fairly well, again, with these constraints. And at some point, we'll probably release these constraints and allow it to deal with a wider choice of phasing patterns. Right now, the phasing patterns are pretty much limited, and they're fairly simple. We may at some point increase the measures of effectiveness that we use for the evaluation. But right now, we're using maximum Q length on every approach. What are our next steps? Well, we're fine-tuning the double deep Q network model for a single intersection. And it seems to be working quite well. We then will apply that model to a grid network with traffic instant generation and emergency vehicle response activity. And of course, that's going to be a much more difficult problem. And the concept is that as we get into the network side of this problem, the amount of storage that we will have will be greater. And again, we hope that it will be handled well with the neural network concept. We're using neural network now for the single intersection problem. And we hope that we'll be able to deal with the grid network problem. And again, we're not working with a very large grid network, but with the grid network problem, we hope that neural network will work for us. Questions?
Okay, does anyone have any questions for Dr. Machemehl? We have time for one or two questions.
Hi, Professor. I have just a simple question. Did you assume that all vehicles to be connected vehicles, so the intelligent signal can get all information from the vehicles?
No, we did not. We did not assume any connection with vehicles at all. I have a colleague here at UT who has a very nice signal timing plan that works, that's really wonderful if all vehicles are connected. But we're probably not going to have that situation for a fairly long while. And so we're working this problem as if none of the vehicles are connected. And so the controller cannot get any information directly from the vehicles. We have to do it with an external sensor. And so again, many vehicles are connected now, but I think it's going to be unlikely that all vehicles will be connected anytime in the not too distant future. And of course, that's going to require, in order for all vehicles to be connected, that will require, I guess, policy action by the federal government that will require all those of us who have old vehicles to purchase some kind of an add-on system that will make our vehicle connected. And I think there's going to be some reluctance to the government to do that. So at any rate, I think we're going to have, in the future, we're going to have some autonomous vehicles, some connected vehicles, and some fraction of the fleet. Again, we saw in the first presentation up here, the fleet turnover is pretty slow. It takes about 20 years for the fleet to totally turn over. So I think we're going to have, for the next couple of decades, a combination of connected, autonomous, and unconnected and non-autonomous vehicles operating in the system, and the system has to be able to accommodate all of that. If we could assume all vehicles were autonomous or all vehicles were connected, it does simplify the problem quite a bit, but we're not doing that.
Okay, I'm going to have to cut it off there. I just realized what time it was. For various reasons, I was blanking out on how much time we have left in the session. So we're going to have to wrap it up there. There is one question in the chat. Dr. Machemehl, you could maybe answer that question offline.
Sure.
From Yang Zhao. It went to the host and panelists chat. So anyway, let's move on. We're going to move on now to the fourth presentation in the session, which is by Dr. Jin Zhu at University of Connecticut. Let's see, and her presentation is about exploring the impacts of transportation system on human behaviors during disasters using mobility data.
Sure, thank you, Dr. Ivan. Let me try to share my screen. Can you see my screen?
Yes.
Okay. Good morning, everyone. My name is Jin Zhu. I'm assistant professor in Civil and Environmental Engineering Department at University of Connecticut. Today, I'm going to make a presentation on exploring the impacts of transportation system on human behaviors during disasters using mobility data. I would like to thank my graduate student, Shrita Chowdhury and Zhenzhen on their work on this. A little bit background. So a comprehensive understanding of human mobility pattern on the disaster is crucial for strategies aimed at improving community resilience for a variety of reasons. We know that in the face of disaster, we all have a variety of transportation needs, from evacuation, which obviously is a very important thing because it moves people away from high-risk areas to safer areas during natural disasters, as well as any other activities. For example, before disaster really hits, you may want to go to grocery stores to purchase some food and water, or after disaster, you may need to go to purchase materials to do some cleanup work, or you want to check a friend, a family. So having an effective transportation system is really important to help people to cope with disasters. And a specific question we want to investigate in this specific study is, would the level of diversity of a multimodal transportation system affect human behaviors in disaster? We know that this center is all about multimodal transportation and diversity. And this is really the trend of future direction. We want to have a combination of different transportation modes, including cars, buses, bikes, railways, scooters, shared vehicles, to provide us a variety of choice, so we can be more resourceful when we have different transportation needs, especially when we're facing some difficulties such as disaster. So we want to understand, would that level of diversity really affect people's behavior and really help people to cope with disasters? When we started this, trying to answer this question, we did some literature review, of course, as a first step, and we find out there are mainly two streams of study. One is survey-based study. So this is traditional way we understand people's travel behavior, for example, through survey or interviews. The benefits of this stream of study, of course, is we get to know individual level behavior, such as evacuation behavior, reflected in their answer. And since we can ask a lot of like background information, even ask their decision-making process or their, a variety of factors at household or individual level, we get to know obtain the insights on variables that influence human travel behavior during disaster. This is an advantage, and there are some challenges regarding this stream of study. Is the difficulty in collecting large volume of data. Collecting such large amount of data obviously is very costly. It needs a lot of time and effort, and of course there's another challenge we need to deal with is there may be data bias in this kind of data we collect, because either we need to ask some hypothetical scenarios and ask them what choice you will make, or this kind of data collection is retrospective. Then people need to make sure they remember how they make transportation choice, or how they do certain transportation, how they do some certain evacuation behaviors during disaster. But of course, this is a very useful way of study. Another stream as an emergent trend of study is location-based study. So because of the development of technology, now we can rely on a lot of accurate location-based data, either from GPS-based smartphone location data. So nowadays, a lot of time, if you pick up your smartphone and use a certain app, it will ask you, would you allow me the app to track your use your location data, etc. Once you hit yes, it will track your data. Of course, it's not like there's many privacy issue related, and we don't like it to track our data all the time. But of course, it provides us a new way to understand people's travel behavior. Another type of this kind of location-based data is from social media. So when people use social media, sometimes they have geotagged, for example, tweets, or in Facebook, they can share your location. So this is another way for us to understand the human behavior and mobility. So the benefits of this stream study is it provides massive spatial temporal location points for us to understand the phenomena. So this is so-called the benefit of big data. And it can help us to have accurate knowledge mobility pattern during business as usual and disaster periods, because it's not rely on people's answer. It's based on their real accurate behavior. So that's why we choose this second stream, using location-based data to help us to understand the question, would the multimodal transportation system and its diversity affect human behavior, travel behavior during disaster? So we propose 3 steps of study as a small prototype study. So step 1 is data collection. There are many third-party providers provide this smartphone location database. For example, the one we choose is called SafeGraph. Main reason we do this in this prototype phase is it's free for academic use. So SafeGraph provides anonymized point of interest data from USA, Canada, and UK. So point of interest data is defined as a place you spend time or money. For example, there are many points of interest: schools, stores, retailer stores, any community centers, or church, etc. They are all point of interest. As long as it's a place you spend time and money there, it can be recognized as a point of interest. So SafeGraph basically based on smartphone users, it collects such data. And in general, this data set review trends in visits to point of interest, like the counts of visits to specific point of interest and the time you spend there. The number of visits each day and overall visitors to point interest from different geographic areas. So it also tells us where these visitors come from. There are different data sets in SafeGraph that provides, including core place data set. This is a basic data set, including like what is that, the location name, categories of that point of interest, the brand associated with point of interest, and how long you spend time there, etc. So this is a basic database. And SafeGraph also grouped their data set into different formats. For example, there are two other data sets, geometry data set. So in geometry data set, they provide the pure point of interest footprints with spatial hierarchy, like they categorize different POIs with a hierarchy structure. For example, restaurant may belong to some retailer sector, or schools, or specific schools. They are all belong to education, etc. And then they also have a database called a patterns dataset. So in patterns dataset, SafeGraph help you to do some analysis to provide certain trend. For example, how often people visit a certain place, how long they stay in a certain type of place, where they come from, etc. So this is the source of data we use. Second step is data processing. So we process the data specifically based on our needs. So first, we want to know whether this kind of how people behave during disasters. So we identify certain natural disasters, and then we capture and we extract this data, mobility data set from the database related with those the period of disaster. So we do not only capture the human mobility data, POI data on the disaster day. For certain disasters, we also capture the day before and the day after disaster, because a disaster does not only affect on a certain day, it may have like a period of influence. And then because we want to understand whether the multimodal transportation system affect human mobility, we basically organize the data based on zip code areas, because based on a previous study, we developed a methodology to quantify the level of diversity in different zip code areas. So by grouping the mobility data by zip code areas, later we can compare the human mobility trend in different zip code areas with varying levels of diversity of multimodal transportation, and we can answer the question whether the level of diversity in zip code areas matters in face of disasters related regarding the mobility. So the third step is what kind of analysis we do. So as I said, there are two purposes. One purpose is first we want to know whether this human mobility data we use can actually reflects a difference, right? Whether there are difference in business as usual days or in the days when people are coping with disasters. We have a gut feeling that it can reflect, but we also want, as a first step, when we analyze our data, we want to see whether there's really a difference. Second step is we want to explore whether that level of diversity matters. So in order to answer these two questions, we develop a simple equation. This is called mobility change. So this mobility change, there are two variables in this mobility change equation. One is mobility disaster. So mobility disaster basically is observed mobility during a disaster day. When in the selected disaster day, we captured the number of visitation in point of interest on that day across different zip code areas we select. And the second variable is called mobility baseline, because we want to know whether there's a difference, right? So we want to build a baseline. So how we build this baseline? Using the disaster day, based on that disaster day, we selected other same days within the same months. For example, if the disaster day we choose to study is a Tuesday, then in order to have a baseline on the normal mobility in this zip code area, we select other Tuesdays in the same months. So and calculate the average. In this way, we know baseline of the average mobility. And then this mobility change basically is a mobility disaster minus a mobility baseline divided by mobility baseline. So we get a percentage to know to which extent the disaster affect human mobility and reflected in this point of interest data. So this is a simple methodology, very straightforward. And we tested the proposed methodology in the case study. So we used Connecticut as our home state to do this case study. And we selected 2 disasters. One is a thunderstorm occurred in Connecticut on May 15th, 2018. This thunderstorm basically includes 4 tornadoes and widespread damaging straight line winds, which produced one of the most severe weather events in Connecticut in decades. It caused about 23.7 million in damage and cleanup costs for state and local government in Connecticut. And the second disaster we choose is a tropical storm, Isaias, occurred on August 4th, 2020. It's a more close event. It's a very damaging event. It's a tropical storm. It's not even at the hurricane level, but the damage, of course, is very significant. Approximately 9,000 trees fell into power lines, streets and homes. More than 90 state roads were closed, along with hundreds of local streets. And a lot of places in Connecticut during that time went out of power, as I mentioned, because its trees fell on the power lines. As a personal experience, my home went out of power for almost a week, and it's really a terrible experience. So the grand total in damage to public and private infrastructure due to this event last year was approximately 230 million in Connecticut. So both of these events are significant, like they cause a lot of damage. And we choose these 2 for another reason, because these are 2 types of events. The thunderstorm, there is like no early warning. So I believe they only issued a warning like a couple of hours. So it does not provide a lot of time for people to prepare for it. In contrast to that, the hurricane, not hurricane, it's actually tropical storm Isaias. It has warning, like people usually know for this kind of tropical storm hurricane, it has a pass, although it's uncertain, but you can prepare like even days before that. So regards with 2 events, we collect the point of interest data. So these are the data we collected from the SafeGraph database. So basically, you can see that for the first one, the table 1, we collect the data on each day of May 2018 and organize them by 6 zip code areas in Hartford, city of Hartford. And then the same thing, similarly for the Isaias for August 2020, on each day we collected the point of interest visitation data and organized them by the 6 zip code areas. And some quick observation by looking at this data, you can see that in 2020 August, in each zip code area, in each day, there is a significant decrease compared with May 2018. It's not directly relevant with our study, but there's an obvious reason because of this. And this is a quick validation to see, okay, these data are really providing some insights. The simple reason is COVID, compared with 2018, 2020, because we're still being affected by COVID. So you can see in each zip code area, the visitation number has a significant decrease in the same zip code area compared with 2018. So as I mentioned, that is not directly our purpose. Our direct purpose is to using the equation we propose on disaster impact to see whether what's the difference of mobility in each zip code area due to disasters. So this is analysis we do. So first analysis we do related with the thunderstorm we mentioned in 2018. So here we have 2 figures. So I first want you to see the figure on the right. So the figure on the right is not from this specific study, but I presented last year. It's a study we do to quantify the level of diversity in multimodal transportation systems in different zip code areas in Hartford. We also use City of Hartford as a case study. So you can see that in these six zip code areas, based on the physical infrastructure condition, we considered like the roadway network, railway, bike lane, etc. We calculate their level of diversity based on entropy method, and we plot them here. So you can see 06103 has the highest level of diversity. This is a downtown area of Hartford, followed by 06105, 06106, 06120, and then finally 06112 and 06114 has the lowest level of diversity across these 6 zip code areas. So this can provide us an understanding of level of diversity. And then the figure on the left, it's a result we get from the mobility data from SafeGraph. So for this thunderstorm, we captured a 2-day of data. One is a mobility change on the disaster day, and one is mobility change after the disaster, 1 day after disaster day, which is May 16th. So we didn't consider mobility change before the disaster because, as I mentioned, for this thunderstorm, there's no preparation or really early warning, so people cannot really prepare for that. So we only want to know on the disaster day after it happens, and 1 day after it, what's a change in human mobility. So we can see that overall, you can see in these two curves, all the data show all the mobility change showing a decrease, except for one data point here in 06103 on the disaster day on May 15th, 2018. There's an increase on this day. One reason for this increase, we think, is because 06103 has a high level of diversity. So after it happens, people can still use, and people are willing to use, a variety of transportation mode to evacuate or find a shelter or go home. So they can still cope with this. Sorry. And for other zip code areas, because of a limited choice of transportation, it may be more difficult compared with 06103 for them to make certain transportation or travel in the face of this thunderstorm. Especially, we can see that in 06112 and 06114, these are the 2 zip code areas with the lowest level of diversity across these 6 zip code areas. They are decreased in mobility, no matter on the day of disaster and 1 day after disaster, are lowest. So, so from this, we can have a very preliminary kind of observation. Higher transportation infrastructure diversity could result in a comparatively lower effects on evacuation choice of people's mobility during and after disaster. So we move to the next disaster we studied is the tropic storm Isaias on August 4th, 2020. So again, the figure on the right is the same. We have the level of diversity based on physical infrastructure conditions in these 6 zip code areas. And then on the left, we plot the data related with mobility change. On the disaster, 1 day before the disaster day, on the disaster day, and 1 day after disaster day. So before the disaster day here, we capture this information because we know that people can prepare for it. And usually in hurricanes, people really could have more, travel because they want to go to, as I mentioned, purchase some food and water, or do some preparations. They may drive to a friend's house to get a better shelter, etc., if they feel like their home is not safe. Or in contrast, if a place is not really have a limited, or people have limited transportation needs, that fear of the hurricane coming may also prevent them making certain travel plans. So we want to understand, even before the disaster, on the disaster, and after disaster, what will be the change in mobility. So from this figure, we can see that in most situations, again, higher level transportation infrastructure diversity lead to high evacuation mobility or behavior. We can see that there are more like positive mobility change values in this case, because especially before the disaster day, we can see that people are making more trips. But we can see that again in 06112 and 06114 as 2 zip code areas that have the lowest level of diversity in the transportation modes, they all show decreasing transportation mobility. They are all negative values before the disaster day, on the disaster day, and after disaster day. We think it's because these people have limited choice in this situation. Also, we see that an interesting point, which is a little bit counterintuitive. We see that in 06103, we mentioned this zip code area, it has the highest level of diversity. So as we mentioned, in most of the case here, before the disaster, on the disaster, after the disaster, all zip code areas, many zip code areas here show an increase in trend because people could prepare for it and people may make more travels during the stay. But we see that on the disaster day, 06103 actually showing a negative value here in their mobility change. And one potential reasons we explored and guessed is because people in this zip code area, because it's a downtown area, people may not need to come to this area for work, or people living these areas, they may have better preparations or maybe find shelters beforehand. Because they may have higher, income, or they already have like higher transportation infrastructure diversity in this zip code area, so they can even do preparations even earlier than this one day before this disaster. So this is pretty much the preliminary result we find out. This is ongoing research, and as I said, this is like we cannot even call it a conclusion yet. It's based on, I'm only showing you 2 case studies and showing some preliminary observation. So from this preliminary observation, we can see that the results suggest that if the transportation infrastructure diversity is comparatively higher, there is a higher chance, a possibility for people to better cope with disaster due to ease of access to different transportation modes and ease access to different point of interest in different ways. As future work, we are working basically on more case studies and more ways to analyze this data, such as advanced statistical models and network analysis. So, for example, we can use network analysis to incorporate more information into this analysis, such as where people, what's the origin of people, and we can incorporate the social demographic information from Census Bureau, so we can better understand people's behavior with the influence of disasters and link it with the transportation system. So with this, I conclude my presentation and I will come to questions.
Okay, so we're out of time in the session.
Sorry.
We're over time and there's no time for questions because the next session begins in about 5 minutes.
Oh, sorry.
And I have not done my presentation. So Wei, I'm not sure how you want to handle that situation. Is it okay for us to run over a little bit, or how do you want to?
Yeah, sure, John. Yeah, please go ahead and make your presentation.
Okay, all right. I'm going to do it fairly briefly, but anyway, but I didn't want to have any questions. In any case, there's no time for that. So,
Sounds
all
good.
right.
Thank you.
So I'm going to go ahead as soon as I can get this queued up, and I have to find. How do I get that back now? All right. I think I'm sharing now. Maybe no, I have to click one more time to get to share. I always forget these things. There's so many. All right, why is this not coming up? All right, I'm trying to get this to share. Oh, now I can't find Zoom anymore. Oh, there it is. Okay, I'm trying to share. There, one more click. All right. Okay, can everybody see my presentation?
Yes, we can see
Okay,
that.
good.
Yes,
Thank you.
yes.
All right, good. Thank you. I usually use another platform rather than Zoom, and so whenever I switch to this, it's always a little different. So, all right. So I'll just try to go fairly, give you a elevator version of this. So we're looking at is estimating pedestrian compliance at signalized intersections, and we're looking at demographic and geographic factors that will can help explain that. So I'm just going to go through the motivation pretty quickly. Basically, with pedestrians are pretty much we're trying to encourage pedestrians and walking and using other kinds of public transportation and so forth to improve, reduce greenhouse gas emissions, et cetera, and increase livability. But we have to accommodate pedestrians at traffic signals. And one of the things about pedestrians is that they really are not as compliant with traffic signals as motorists are for various reasons, one of which is that it's very rare to actually enforce pedestrian compliance as compared with vehicle compliance. And so it's helpful to learn what about the conditions where pedestrians are not compliant. In other words, we want to try to understand a little bit better what kinds of characteristics result in the more non-compliance. So we collected data. This is largely a lot of the data we're using, actually all the data we're using were collected from another project where we are looking at observations of interactions between pedestrians and motorists. And so we're using those data, but we also in a project last year where we used some of those data looking at pedestrian volume, we collected some additional GIS land use and coverage data to augment that data. And so that's what we're using. But for this particular project, the information we have about the compliance with signals is really limited to 4 towns in Connecticut: Hartford, Manchester, New Britain, and West Hartford. And so some of the data that we gathered, we have the pedestrian volume and crossing behavior data. So we know the signal indications at the time of the crossing, and also if they interacted with motor vehicles, which we're not using in this study. And then we also have, so from the signal indications, we can determine if they were compliant or not. And then we also have geospatial and street network data. So we know some this other information was collected, and we're not using all of this either from this particular project. So here's some summary statistics of the land use. So we're looking at both area and the count for different high, mid, and low density land use areas. And we also have a weighted population density at each of these locations. And so this is some samples of those statistics. So what we're doing is for each pedestrian that was observed, we are predicting the probability of them complying. And we're using a logistic regression where we have, it's a function of variables describing the pedestrian, the physical crosswalk location, and then the geospatial variables as well that are estimated. And this just gives you, the graph on the right just gives you an overall view of this. So that we had two different types of pedestrian signals, which is the previous study was looking at a comparison between those. And so we're just accounting for that here. Concurrent signals means that the pedestrian crosses at the same time as vehicles having a green light in the same direction. And then the exclusive means that there's an exclusive phase for pedestrians, and where all the traffic stops and pedestrians get a walk signal and all the drivers have to stop. And now I'm showing 2 different bars here. So the strict compliance at an exclusive phase means that the pedestrians only crossed when the walk signal is showing. Relaxed compliance means that the pedestrians may have crossed on the walk or maybe on the green light, because what we find a lot in Connecticut is that when the light is green, there's no vehicles turning, a pedestrian will frequently not wait. And so we just calculated that as saying if it was a concurrent phase, that pedestrian would actually be compliant. So that's what we're calling the relaxed compliance. We're not actually referring to that, and I'm not going to refer to that in the study today, but one of the things we note here, just right off the bat, is the concurrent signals have much higher compliance than the exclusive phasing. So we have a preliminary model. We don't have a lot of results to show yet because we've got started late on the project, but these are some of the results. We have those. Oh yeah, so I wanted to say also the geospatial network data were collected with 3 different buffers around the intersection. So we're looking at what was happening around that intersection within 1/8 of a mile, walking distance, quarter mile, or half mile. So we have model estimated using the variables for all three of those. And so these are the results. I just want to jump right up here to the preliminary findings since we're out of time. So what we found was that factors that increase the pedestrian compliance are, first of all, having a concurrent rather than exclusive ped phasing, which I already mentioned before. If it's a 25-mile-per-hour speed limit compared to 30, the compliance was higher, which I found. Then the 35-mile-per-hour speed limit seems to be decreasing it, which is kind of surprising. You'd think it would be the opposite. So we're going to have to do some more investigation about why that's happening. And also the low density development seems to be the base. So medium density is higher compliance, higher density has lower. And I'm going to come back to that in a moment. Higher population density in the area it decreases the compliance, and higher pedestrian volume in the crosswalk decreases the compliance, but there is a leveling off trend, which we see with a negative, with a positive on the squared of the volume. Interestingly enough, if we have a two-way street or a one-way street that's exiting at that intersection compared to a one-way street that's entering at that intersection, that increases the compliance. And then senior pedestrians are more compliant than others. And so what our overall conclusion so far with this preliminary results is that pedestrians appear to be less compliant when there are more of them, and when the area is denser or is more relatively undeveloped. So the two extremes there. And this kind of makes sense because if there's a safety in numbers kind of a thing there, when there's a lot of pedestrians, they're more likely to not worry about being compliant and traveling and crossing when they're not supposed to. And the same thing with an undeveloped area, there's probably related to how many vehicles there are as well. And also just the idea that they don't really need to be concerned. And also pedestrians are more compliant when the crossing task is more complex. So for example, you have the two-way traffic, or when you have the concurrent phasing. So you see that now that they have to watch for the vehicles turning. And anyway, it seems like the pedestrians seem to be more compliant in those situations. And then the senior pedestrians are more compliant than younger pedestrians, probably because they need more time to cross the street. And so they're also going to be exposed for much longer time while they're in the streets. So they want to be sure that they're going to be safe. So our future work, we're including some more pedestrians, more locations that are still being observed on another project that's going on that we're doing for Connecticut DOT. So we're going to add those in and collect additional data for that. And we're going to do a bit more analysis as well once we have all the data collected to dig into these things a little bit more carefully. So I'll just wrap it up there. If anyone has a question, I'll be happy to take it. I think we should probably move on. I'll let you all go on to the next session. If you have questions for me, you can send them to me offline and I'd be happy to answer. So that was a rapid explanation of this research. So thank you everybody for attending this session. Those of you who are left, I think let's just wrap this up so we all can move on to the other sessions in the conference. Thanks for the opportunity. I thank you all. Thank you to the speakers for giving presentations of their interesting research, and thanks Wei for organizing the seminar. So.
Okay, thank you, John.
Thank you, everybody. Bye.
Thank you. Yeah. So the next moderator is here, Dr. Qi. Do you want to move on directly to next session, or we take maybe a couple minutes break? It's up to you. Yeah. You're muted, Dr. Qi.
Can we have a couple minutes break?
Yeah, sure. Yeah.
Yeah. Okay. So
yeah, we come back at 10:40. How about that?
That's okay. Yeah.
Okay. Okay. See you there. Yeah. Thanks.
Thank you, everybody. Bye.
Yeah. Thank you, John. Yeah.
Bye.